Introduction to Thermochemistry is filling in. There are 3 video lectures up. Video lecture 4 is from a week ago Thursday. Video lecture 5 is from last Tuesday, excuse me. And video lecture 6 is the equivalent of what would have happened last Thursday if you were in the room to hear it. Okay, so I promised that would go up on Friday morning. It went up on Friday morning, but if you haven't seen it, it will actually fill in some of the details I'll be talking about today a little bit better in a little bit more detail. I'm going to try to select the topics in this particular lecture so that if I do them in reverse order, you can actually get benefit out of both ways. Okay? But they surround my definition of enthalpy. And I'm going to redefine enthalpy here in a little bit. There's also plenty of homework online. The standard exhortation is do more homework. If you've done all the homework, God bless you. I just released section 9.4 homework this morning, do more homework. Okay? But if you've done all the homework up through 9.3, that puts you in the vast minority of people. Most everybody can benefit from doing more homework, especially since we're getting this practice assessment out of the way, because a real assessment must be coming up soon. This is the 4th week of the course, and I need to make sure that I have some assessment done if I want to get 3 assessments of this in and on this course. Okay? Let's remind ourselves of one definition. Heat transfer is the quantity we represent with the letter Q. We've done this many times before now. Okay? It's a process energy. Because it's a process energy, there's no such thing as delta Q. I don't ever talk about a change in heat of a stuff. And because there's no such thing as delta Q, there's no such thing as Q initial or Q final either. I don't talk about initial heat possessed, and I don't talk about final heat possessed. I simply talk about heat, and so far in what we have studied, the expression of heat transfer that takes place happens when we observe one thing starting at one temperature and changing its temperature to a different temperature. There will be other signatures of heat transfer we talk about later in the course, but that's our major signature of heat transfer right now. And when we get into the lab this week, we will see an example of this kind of heat transfer. So I want to make sure I've presented in full a new symbol that we're going to use in the representation of energy transfer. And it's an alternate way to describe energy transfer when we put it into context of chemical systems. It's represented by a capital H, and this quantity is called enthalpy. Now, there are many ways that I can describe enthalpy, but the way I want to make enthalpy plainest to everybody is I want to represent it as a heat transfer at constant pressure. And if I can control the conditions under which I'm doing this heat transfer, I can describe this enthalpy not merely as a property of a process, but as a state energy. And because I can describe this enthalpy as a state energy, what that means is I can talk about different conditions under which I actually generate this quantity and how this quantity changes over time. I can talk about a system like this possessing some enthalpy in its initial state. I can talk about a system like this possessing some enthalpy in its final state. Okay? Now, this quantity enthalpy is typically associated with chemical reactions. If I'm describing heat transfer and just in terms of something getting cooler and something getting hotter, there's no chemical change that's taking place there, right? There's nothing going on that is shifting something that's possessed by one thing to another thing. The only thing that's going on there is temperature of one thing is falling, temperature of the other thing is rising because heat is being transferred from the one thing to the other thing. Okay? But let me talk about a chemical reaction. Let me use as an example of such a chemical reaction something very, very simple and straightforward. Let me talk about taking elements in their standard states and forming a compound from them. Excuse me. How do you go about making water from its elements? What are the reactants that come together to make water? If those reactants are elements. What's the formula of water? H2O. What are the elements that make up water? Hydrogen and oxygen. Sure. Now, when we come across hydrogen in nature, how do we come across hydrogen? As a gas. How do I write down the chemical formula for hydrogen as a gas? Why is it H2? Because hydrogen, like other gases of its sort, are diatomic. Okay? And how do I write down oxygen? Same way. O2, absolutely. Okay. Now, how do we come across water in nature? As a liquid? Is that always true? How else could we come across water in nature? It's a gas. So I could actually tell this story two different ways, couldn't I? I could tell one version of this story for water as a liquid. I could tell a completely different version of this story for water as a gas. Okay? Now, how do I go about balancing this equation? Because I've just written this up here on balance. I need to balance it. How do I go about balancing this equation? Two in front of the H2O, and then, okay, yes, that's a nice grade school way of balancing a chemical equation. Thank you, I hate it. Okay? I don't want to balance the equation that way. And I recognize that it might be very nice and convenient for you to write down this 2. Okay? Don't write down the 2 yet. Okay? Because I actually have another way I prefer for you to balance this. Let me make sure this is plain. When you actually see that equation up there balanced that way, how do you interpret that? What does that mean to you? And this is not a trivial statement. How you actually read this equation matters a whole lot to what I'm going to do next. What does 2H2 represent? You say moles of hydrogen. Do you naturally think about this as moles of hydrogen, or do you think about this as something different? What do you think about it as, Wyatt? Quantities. If I'm going to boil quantities down to its most basic part, what quantity am I going to be referencing? Yeah, the individual molecules themselves, sure. Okay, 2 molecules of hydrogen combined with 1 molecule of oxygen yields 2 molecules of water. But Avery using moles is important here. 2 moles of hydrogen gas combined with 1 mole of oxygen gas to make 2 moles of water. Okay? It's important because when I actually balance equations like this, I want my product in this type of a reaction to be a single mole. So I don't like this balance. This is the balance that I prefer. Do you like that, Avery? Why don't you like that? Okay, just I don't like fractions. What's uncomfortable about fractions in this particular case? Right. Now, you just went, you said moles up front like a good chemist. But I put that half up there, and you just lapsed right back into the grade school. I don't like to think about half a molecule thinking. Okay? This is why the interpretation of the chemical reaction in moles is so fruitful. 1 mole of hydrogen gas plus half a mole of oxygen gas yields 1 mole of water as a product. Okay? I really want you to lean upon that molar interpretation of the chemical equation, because that molar interpretation is what's going to be really fruitful for our study of these reactions in terms of what's possessed on the reactant side and what's possessed on the product side. Okay? I swear to you, for those of you on Zoom and for those of y'all who are watching the video later, that was a really fruitful classroom discussion. I hope by reacting to it the way I did, that I brought at least some of that flavor out. But I really want you to think about interpreting these equations with the coefficients representing moles and not molecules. And I meant to represent this second equation as H2O in its gas phase, because that's what we were talking about when we were talking about our different possibilities. Okay? These two equations are examples of reactions of formation. And by formation, what I mean is taking some substance and forming that substance from the elements in their standard states. Okay? Now, H2O in its liquid phase and H2O in its gaseous phase have values of enthalpy that we know and can tabulate. And what I want to make sure that everybody sees in the course is that underneath the introduction to thermochemistry, as you go through all of the different topics and you get ahead of the section 9.4 homework, there is a tabulation here. It's labeled standard thermodynamic data. I have put this file of standard thermodynamic data together, excuse me. And I've put it together based on your textbook. I've placed it together based on data within Sapling that's usable on solving the homework. I've put it together based on other resources as well. Let me click through and show you what this looks like. Okay? There's a preface to this thing that tells you where I got this thing from. And there are all sorts of chemical substances in here, listed in all sorts of ways. And there are 3 different columns of data for each substance. The 2 columns on the right labeled delta G and S, I'm not ready to talk about yet. I'll be ready to talk about them later. But this first column, delta H, is a column I am ready to talk about now. Because delta H represents an enthalpy change. It represents energy that's released in the formation of a certain substance. Let me keep scrolling down and find water. I'm going to find water under hydrogen. All of the elements are listed in alphabetical order. And here is water. And you'll notice when water is listed in this tabulation, it's listed two different ways. One way is as a liquid, and the other way is as a gas. And there are values underneath the delta H column characteristic of water as a liquid and water as a gas. Let me put this tabulation into the notes that I'm doodling on the whiteboard. When water is formed in the liquid phase, the standard delta H of formation is negative 285.83 kilojoules per mole. Note how I write this down. Delta H degree F. The degree symbol stands for standard. F stands for formation. And by standard, I mean it's standard ambient conditions. 25 degrees Celsius, 1 atmosphere of pressure. Okay? Meanwhile, for gaseous water, for water vapor, the standard enthalpy of formation is negative 241.8 kilojoules per mole. Okay. Per mole of what? Not, it would work for hydrogen as it turns out, but that's not what the intent is. Water. And in fact, the major reason that I prefer this balancing of the chemical equation for water is to keep a coefficient of 1 in front of H2O liquid and H2O gas. And to say each one of these standard enthalpies of formation represents energies per mole of water. Okay? So what this says is if we take 1 mole of hydrogen gas and half a mole of oxygen gas and combine them, we get 1 mole of liquid water and we release 285.83 kilojoules of energy. Or we get 1 mole of water vapor and we release 241.8 kilojoules of energy. We actually release a little bit less energy forming water vapor than we release forming liquid water. Nice little fun fact to toss on. Okay? And we can do this with several other things in the tabulation. Give me a different compound. Somebody name any different compound that we've worked with. Don't you love being put on the spot like this? Carbon dioxide. Let's go to the tabulation, see if we can find carbon dioxide. It'll be listed under carbon, 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 where's carbon? Here's carbon. Right underneath carbon, here's CO2. Okay? And I've got a delta H of formation for CO2 of negative 393.5 kilojoules per mole. Okay? Now, how do I write the formation reaction for carbon dioxide? Well, the product is CO2 in the gas phase. What are the elements in their standard states that make up CO2? Carbon turns up. How's carbon turn up in nature? Diatomic or single atoms? Single atoms. Most solids turn up as single atoms in nature. I put one additional distinction on carbon. It most commonly turns up in nature in graphite, the same graphite that's in your pencils. How do we say oxygen turned up in nature? O2, diatomic. How do I balance this equation? Oh, it's already balanced. We're done. Woohoo. And the value we took from this tabulation is negative 393.5 kilojoules per mole. If I combine 1 mole of solid carbon in the graphite form and 1 mole of oxygen gas, that will yield 1 mole of carbon dioxide, and it will release 393.5 kilojoules of energy. These are all delta H's. Okay? They represent some change in energy from reactants to products. Okay? And that change in energy can connect with a release of heat as long as we hold conditions surrounding that at constant pressure. Okay? And that's my major utility of this enthalpy concept. It represents, if this reaction goes forward, it's going to release heat. And I'm measuring that heat at constant pressure. Okay? And again, to reemphasize, I go into more detail on this enthalpy concept in video lecture 6. Okay? So if you haven't watched that, you might get a little bit additional insight into things by going through that lecture. Okay? Now let's tell a different story. How many of y'all are chemistry majors of one sort or another? None of y'all. Okay? I'm going to keep recruiting. I'm going to see if I can get some chemistry majors out of you guys. But I did tell one story to my 8 o'clock class, and they all wound up being biology majors at heart, even the ones that claimed they were chemistry majors, okay? I'm just going to write down a chemical equation right here. This is solid phase C6H12O6. This is gas phase oxygen. And I'll go ahead and use gas phase water vapor. That should be a yield sign right here. What does that equation represent? What's that? Respiration. Okay. Does anybody see anything different in that equation? Is everybody content describing that as respiration of some sort of form? And now the person who said respiration is shaking her head a little bit. Oh, we can balance this thing. That's fine. That's dandy. Sure. And I'm sure everybody who studied this reaction previously would recognize that and do that balance. Okay. But nobody wants to say they see anything different in this equation. Because if you're content seeing that as cellular respiration, you are a bio major at heart. Okay? And I will vehemently disagree, and I'll say that is the combustion of glucose. That's taking glucose, exposing it to oxygen, and burning it up. Okay? That's the chemist answer. Okay? But yes, Gen Bio 1, if you did your Gen Bio 1 and recognized this well, you recognize this equation from there. Yes. Okay. What's the significance of cellular respiration? What's the point of a cell doing this process? Yeah, we have this stuff, glucose, and that stuff, glucose, has energy stashed away in it. And that energy is being busted up and released, right? And the product of this is a great deal of energy. Now, this is not taking glucose and assembling it from its constituent elements, though. In fact, it's quite the opposite. I'm going to need to take glucose, and I'm going to need to break it down into its constituent stuff, and somehow or another build it back up again into the products that I have over here on the right, into water vapor and into carbon dioxide. And somehow or another, the energy I invest in busting up the molecule had better be returned with interest when I form the products. So I want to talk about how we actually can use this new tabulation of data, this list of enthalpies of formation, to come up with an enthalpy of reaction per mole of glucose. Because glucose in this particular balance that Brianna proposed just a bit ago, that's the only one up here that takes a coefficient of 1, right? Everybody else has coefficients of 6. Okay. Let me actually drag this down. And write a note above it for us. Okay. Now, if most processes that we come across are going to be processes that release energy, if we take a big thing like glucose and we break it up, then that process is going to consume energy. It's going to absorb energy, right? Okay. Let's look at what a reaction might look like when we take glucose and we break it up into its constituent elements. Let me see if I can drag this over. I'll line up the arrows a little bit better. Okay. What are the constituent elements of glucose? How do I make up glucose? Carbon and hydrogen and oxygen. We just said before that carbon's standard state is elemental or diatomic. Carbon's is elemental. And hydrogen's standard state is, that's diatomic. And oxygen's standard state is, that's diatomic. Okay? How do I get this balanced, by the way? Did I do this last week this time? If I didn't do this last week this time, I did this in video lecture 6. Now, this is not a formation reaction like what I had before. This is the opposite of a formation reaction. I'm going to dub this type of reaction a deformation reaction. Something that's the opposite of a formation reaction. Something that takes a constituent stuff and breaks it down into its elements rather than take the elements and build it up into some new stuff. Okay? But I can still look up glucose in my tabulation and I can still find its standard enthalpy of formation. Standard enthalpy of formation is negative 1273.3 kilojoules per mole. Now, that much energy is released when you build up glucose. So, when you break down glucose, when you deform glucose, what's true of the energy in that case? It's not released, it's absorbed. I'll write it down this way. Standard enthalpy of deformation is going to be something that's a negative of standard enthalpy of formation. Okay. Now, that gets me 6 carbons, 6 hydrogens, and 3 oxygens. I can also talk about breaking up 6 oxygens. If you really want to be complete about things, you can write down 6 oxygens broken up. But if I was going to break them up, I'd break them up into their elements in the standard states. What's the element of oxygen in its standard state? O2. In the inimitable words of Slappy Squirrel, that was pointless. What's the enthalpy of formation of O2? I can actually look that up in the table. I can scroll down to the values I had for oxygen in the table. Oxygen, here we go. And right up top, right at the very top, I have oxygen in its standard state. And its value is 0. Okay? That's characteristic. It turns out that for any stuff you ever come across, if you need to know what its standard state is, you can just look at this tabulation and come across the first entry for that element in its tabulation. That will be the element in its standard state. And you will see that the enthalpy of formation for that element in standard state is 0. Which means its enthalpy of deformation will be 0 in the same way. Is it necessary to even write that? If you want to have it written down, that's fine, that's dandy, that's wonderful. I have a limited amount of space, so I'm just going to go ahead and erase the whole lot. And I'm going to take those specific elements and I'm going to put those elements back together again to make the compounds on the right side of the chemical equation. And we've talked about these reactions already. Remember that this is water in gas phase, so I need the negative 241.8 kilojoules per mole value for it. Negative 393.5 kilojoules per mole for carbon dioxide. Pearson, how'd you remember those without looking them up? Number one, I've been doing this for 20 some odd years. So some of these values come into my brain immediately. Number two, I just did this example in the lecture previous. So I've looked these things up already this morning more than a bit. Okay, look at one thing very closely though as we went through and do this. Let me make sure my arrows are lined up as closely as they can be. Don't clear canvas. How many moles of water and how many moles of carbon dioxide am I making here? 6 moles of each. So what I need to do with these equations is I need to multiply through the equations by 6 in order to represent. And if I'm going to get 6 moles of water vapor out here, I've multiplied this by 6. I've got to multiply everything by 6. I've got to multiply this by 6 here. I've got to multiply this by 6 here. And I have to multiply the enthalpy of formation by 6 here. By the way, 6 over 2 is what? Okay, let me just replace that with a 3. And likewise, if I need 6 moles of carbon dioxide, I multiply that by 6. I got to multiply everybody by 6, which means I'm putting a 6 here, I'm putting a 6 here, and I'm multiplying this by 6. Now, let me do one other thing here. Because what I have are 3 chemical equations going on more or less all at once. Okay? And if you look close at how I've presented these chemical equations, I can add these equations up algebraically. And if I add the equations up algebraically, there's going to be content in these equations that can cancel one another out. As you look at all 3 equations, do you see something on the left side of one equation that appears on the right side of another? And it appears in exactly the same way. It's not just that the element appears, but the coefficient in front of it appears in the same way as well. What do you see that appears on the left side of one equation that also appears on the right side of another? If you see it, it's going to be an element in its standard state, as it turns out. When you look closely at how I present all of the elements in the standard state, you see several instances of an element in its standard state on the left side of one equation, showing up in the different equation on the right side in a position where it can cancel. What's an example of this that you see? What are the elements that make up glucose again? Carbon, hydrogen, and oxygen. Look here. I've got 6 carbons on the right side of this first equation. Do you see 6 carbons on the left side somewhere else? Third equation down here, right? I can cancel that if I'm adding the equations up. Okay, what else do you see that acts in the same way as that? Oxygen. Where do you see the oxygens in ways that they can cancel? First and second equation, I got 3 oxygens set up here in the first. In the second equation, I've got 3 oxygens. I got 6 oxygens down here, but that doesn't match up with anybody else in the same way, right? So let me cancel out the 3 oxygens like so. What else do you see? Hydrogens. I've got 6 hydrogens in the first equation. I've got 6 hydrogens in the second. They can cancel. Y'all see that? Okay. What I want you to look at is what I didn't cancel out. I didn't cancel out the glucose. I didn't cancel out the oxygen, the 6 oxygen from the third equation. I didn't cancel out the H2Os. I didn't cancel out the CO2s. Hey, that's my original equation come back again, isn't it? Okay? We algebraically added up the breakdown of glucose and the formation of water vapor and carbon dioxide. And we got our original equation. And we did so putting together these enthalpies that we drew from the table in a way that we can add those up algebraically as well. I can say that the enthalpy change for this reaction is equal to my 1273.3 kilojoules per mole up top here, minus 241.8 kilojoules per mole times 6 minus 393.5 kilojoules per mole times 6. The times 6 for the 6 moles of water vapor and the 6 moles of carbon dioxide that I get out of each summation. I can put that into a calculator and I can add it up. And the order of operation should be smart for me. Should do the multiplication before it does any addition or subtraction. And what I'm going to get out of this story when I get all of this added up is I'm going to get an enthalpy change for this reaction of negative 2,538.5 kilojoules per mole. Submitted. That is a beast amount of energy. And that beast amount of energy is the result of breaking up those bonds in glucose into their constituent elements. And then putting those constituent elements back together again to make water vapor and carbon dioxide. Okay? Now, I go into such detail on this example because I want you to see that chemical reactions are algebraic in the same way that any other set of equations we've ever studied is algebraic. So long as we're studying one of these state energies in the process of their break apart and assembly, like enthalpy. There's actually a law of nature that's associated with this very break apart and put back together again, this algebraic deconstruction and reconstruction of reactants and products. And that law of nature is called Hess's law. I'll frame Hess's law like this. If we know the enthalpy changes for a set of chemical reactions, we also know the enthalpy change for the algebraic sum of those chemical reactions. And we get that enthalpy change by simply adding up all of the enthalpy changes for those particular reactions. We know this because state energies are what are known as path-independent energies. They're energies where it doesn't matter the process by which I go from reactant to product. It doesn't matter whether I go from reactant to product directly or whether I go from reactant to product through breaking down the reactant into constituent elements and building the elements back up again into their products. As long as I'm working with a state energy, it doesn't matter. And enthalpy is a state energy. Now, there's an alternate statement of Hess's law. And that alternate statement is how you will typically use Hess's law to study chemical reactions. That's a lot of words. It's a lot of words presented formally. But I want to make sure that those words are emphasized. The enthalpy of reaction for a given chemical equation. The given chemical equation, the example we just worked through, was glucose and oxygen combining together to form water vapor and carbon dioxide. The enthalpy of reaction for a given chemical equation is equal to the sum of the standard enthalpy changes of formation of the products minus the sum of the standard enthalpy changes of formation of the reactants. And I'll write out in detail what I mean by that. Let me write it out in the same way. I had water first and then carbon dioxide, didn't I? Everybody recognize my big capital letter sigma here? Whenever you see that big capital letter sigma there, what does that represent? Represents a summation. The enthalpies of formation of the products were my negative 241.8 kilojoules per mole for water times 6 minus my 393.5 kilojoules per mole for carbon dioxide times 6. That is the summation of the enthalpies of formation of the products. Minus the negative 1273.3 kilojoules per mole for glucose. And then the enthalpy of formation of oxygen, which is 0. And 2 negatives makes a plus. And I don't remember what the answer was, so let me go through and make sure I've got it right again. I always have to do the computation more times than once. Yeah, really big. 2538.5 kilojoules per mole. Most of the time when you do a Hess's law problem like this, this will be how you do it. Where'd you get negative 241.8 and negative 393.5 and negative 1273.3 from again? You got them from that tabulation of standard enthalpies. Okay. I would ask if there's any questions. I just put a whole lot of accounting in front of you all at once, all in a really obnoxious fashion. More examples would help, right? Section 9.3 of your textbook has plenty more examples like this. But the way that you get used to Hess's law and problem solving surrounding Hess's law is you work examples, you don't just look at examples. And what I think you will find is that the homework problem, the first 7 homework problems, say, in the set that I've assigned for today, give you very, very good practice getting used to Hess's law. Now, the last 3 get confusing because they involve one additional detail that I haven't gone over. And that additional detail is how I actually talk about the energy stored in the bonds themselves. And at its most fundamental level, how I actually deal with these energies comes from the energy stored in the individual bonds themselves. And that's the substance of section 9.4 of your text, which I've not gotten into yet, which I'm going to spend time getting into when we get back together on Thursday. And so I'm going to leave this lecture alone here for today. We'll go ahead and come back on Thursday and do more business then. Thank y'all.